let's go back to Wey's genus 2 surface. So Wey showed that this lives in a one-parameter family, although due to Hauswirth and Trizet, we know it actually lies in a three-parameter family. But within the particular Wey's one-parameter family, let's see what happens. As we go through the family, the size of the catenoid necks shrinks. They get smaller and smaller and smaller. And so we see that Wey's surface limits an affiliation of R3 by parallel planes, which are connected by catenoidal necks. So each of those necks, right here, here, and over here, and these guys as well, shrinking down to a point. Now the location of these points is important, which we'll see. So the limit, we get this noded Riemann surface. The location of the nodes turns out satisfies a particular balance configuration. The limit of Wey's surface is the disjoint union of two copies of the C mod 2 pi I times Z. So the idea is start with a balanced configuration. So here's a balanced configuration with these. We've got 5 nodes on it. They're going to correspond when we open up the nodes to 5 catenoids. So we're going to have these 4 nodes right here will correspond to catenoids pointing in one direction. And this 5th node is going to correspond to a catenoid going out in the other direction. So we start with a noded Riemann surface sigma, each component a copy of the C mod 2 pi I Z. If the nodes provide a suitably non-degenerate balance configuration, then the idea is by opening the nodes, we can get an embedded doubly periodic minimal surface with parallel ends. With this 1,4 example, where we have a 1 neck coming out, 4 necks going in pattern, let's see what happens when we open the nodes now. So this is like these location of the nodes are going to satisfy some special balance configuration. As we open the nodes, we get those catenoid necks, which get larger and larger, get further and further away from the limit. Surface gets pretty interesting, but what we care about is really close to this noded limit, say about right there. What's happening, where we get those tiny catenoidal necks. So we utilize the Trizet regeneration technique. So near the limit, our catenoid surfaces look like a collection of flat annuli connected by catenoid necks. So here I've got these 4 levels. Between the levels 1 and 2, I've got the 1 neck. Between the levels 2 and 3, we've got these 2 necks. Between levels 3 and 4, we have 1 neck. And then between levels 4 and back to 1, we've got these 3 necks, which really are going to attach down here as well. You got to remember we're dealing with doubly periodic surfaces. One of the periods here is going to be this horizontal period in this direction. So the ends are going to go off like this. Got one period in this direction. The other period is going to be this period like this going up. So this whole thing, it's going to just keep repeating. So I could get up to here. That's really identified down there, there, and there for each of those guys. In the limit surface, these necks, these catenoid necks, are going to degenerate to points. And the quotient limit surface is what we call a noded Riemann surface. Each component, a copy of the C mod 2 pi Z with nodes. The nodes have to satisfy certain balance equations. For convenience, the components are identified with the C star, the complex plane minus the origin, via the exponential map. The idea is start with a finite collection of punctured spheres with nodes, such that the location of the nodes provide a suitably non-degenerate balance configuration. We construct a family of Riemann surfaces which form an open neighborhood of the noded Riemann surface. Then construct the Weierstrass data on each of these Riemann surfaces. As each piece of the limit surface is a punctured Riemann sphere, it is possible to express the Weierstrass data on the limit surfaces as rational functions on each piece. Dealing with rational functions makes solving the period problem much simpler. So we can solve the period problem at the limit, and apply the implicit function theorem to solve the period problem in a neighborhood of the limit surface. So that's the basics of how the Trizet regeneration technique works. So we need to utilize the Weierstrass representation in particular for doubly periodic minimal surfaces. So if we let M be a doubly periodic minimal surface, so a minimal surface in the T cross R, then M is diffeomorphic to a compact Riemann surface, sigma, minus a finite number of points. That's due to the work by Meeks and Rosenberg. And there will exist a meromorphic map G, Gauss map, and the meromorphic one form, the height differential dH on sigma, such that if our Weierstrass representation is given by the phi1, phi2, phi3, the 1/2, 1 over G minus G times GH. Phi2 is the I over 2 times 1 over G plus G times DH, and then phi3 the DH. And then we say x of z equal to the real part of the integral of the phi1, phi2, phi3. Then x is a minimal immersion whose image will be the minimal surface M. Again, we refer to that triple, the sigma, G, and DH, as the Weierstrass representation for the minimal surface M. Conversely, let's say we start with the Weierstrass data, the sigma, G, and DH. That will be the Weierstrass data for a doubly periodic minimal surface, in particular with ends 0, 2 pi 0, and the other one, tau 1, tau 2, tau 3, and horizontal ends if the following conditions hold. 1, we'll want the zeros of DH to be the zeros and poles of G on sigma minus the ends with the same multiplicity. We'll want G to have a simple pole or zero at each end. And then we want all the periods. Take the real part of integral over any closed curve C of the phi1, phi2, phi3. We want that to be congruent to 0 mod our two period vectors, the 0, 2 pi 0, and the tau 1, tau 2, tau 3. And that needs to hold for any closed curve C on the sigma. Again, that's referred to as the period problem. So the conditions on the Weierstrass data reduce to the following equations. So here's our kind of prototype surface. I have these around each of my catenoid necks. I've got a cycle. These are labeled with the AK, I. And then I have some other periods, this B12 cycle, this B32, this B33, and then I've got one corresponding to our non-horizontal period on here, this B11 cycle. So geometrically, obviously, we're going to want the real parts of those AKI periods to be 0. The B11, when we integrate along that curve, we want to get our period vector, the tau 1, tau 2, and tau 3. When we integrate along all of these other BKI curves, we're going to want those to all be equal to 0. And then if we do integrate around the punctures, so our punctures, we're going to put them at the 0 and infinity. So at each level, I'll get a different puncture, labeled 0 sub k for the kth level and infinity sub k for the kth level. So integrating along those, we're going to get that period plus or minus the 0, 2 pi, 0. So those will be our conditions, basically our period problem for our setting. So solving the period problem, we're dealing with a disjoint union of noted Riemann spheres at the limit. So we can do complex analysis on these and compute the periods as residues. So much simpler than dealing with the period problem when we're away from the limit, where we can't express our periods as residues as easily. So in the noted limit surface, those horizontal AKI periods given by the following equations, and these are referred to as the force equations. So these PKI terms, those are the kind of locations of the nodes. So when we get a suitable location of the nodes, we'll be able to solve these force equations and solve the horizontal AKI periods. And that's referred to as our balance equations. So the location of the nodes, the PKIs, provides a balanced equation if the force equations, the FKIs, are all equal to 0 for each K and I. Thus, if the location of the nodes provide a balanced configuration, then the AKI periods are all equal to 0 for the noted limit. The non-degeneracy of the balance configuration allows one to use the implicit function theorem to solve the period problem in the neighborhood of the noted limit. So, and we get our main result. If PKI is a set, it's a non-degenerate balance configuration, then there exists a corresponding three-dimensional family of embedded doubly product minimal surfaces that limits as a foliation of R3 by parallel planes. Each surface has the genus G equal to 1 plus the sum k equals 1 to capital N of the n sub k minus 1. Those n sub k are the number of nodes at each level on our surface. Capital N is the number of levels. And they'll have 2 times capital N horizontal ends. So there are n sub k necks between the k minus 1 and k levels, with the location of the necks given by those pki terms. So solving the balance equations. The balance equations, the f sub ki equal to 0, can be combined together nicely into a differential equation. So this result is a theorem from 2016. We'll let the p sub k of z be equal to the product I equals 1 to n sub k, the z minus p ki. So basically it's a polynomial with the roots of those the nodes at the kth level. And then let p of z be the product of all of those polynomials, the pk of z polynomials. Then we get this differential equation given by the q of z. And it happens that this theorem tells us that the force equations will all be equal to 0, that's equivalent to this differential equation being identically 0. It's much easier to solve the differential equation, the q of z equals 0, than to directly solve the balance equations, because one solution of the differential equation corresponds to many equivalent balanced configurations by permutation of the nodes at each level. So, different kind of configurations where we figured out we have surfaces. The simplest type are configurations of type 1, n. So this is where in the quotient we have the 2 levels. Between level 1 and 2, we've got 1 catenoid neck, and then between level 2 and back to the level 1, we have the n catenoid necks. So we'll consider surfaces, these are similar to Wey's surface with 2 levels in the quotient, where so the capital N's 2, n sub 1 equal to 1, n sub 2 equal to n. So in the Wey's surface, that was with the n sub 2 equal to 2. So we'll fix the p sub 1 comma 1 equal to 1. Then the polynomial p1 of z is equal to z minus 1. And then we get our differential equation for q, which is a hypergeometric differential equation. And it turns out it has a solution, p sub 2 of z equal to the sum j equals 0 to n of the n choose j squared times z to the j power. Turns out there's only one balanced configuration of this type 1, n for each natural number n. The KMR surfaces correspond to the 1, 1 balanced configuration. Wey's surface corresponds to the 1, 2 balanced configuration. Note, in most applications of Trezet's regeneration technique, the simplest balance configurations are always given by the roots of polynomial solutions to different hypergeometric differential equations. So, configurations of type 1, n. So if we let the n be a natural number, a1, a2 up through a sub n be the roots of the polynomial, that's sum k equals 0 to n of the n choose k squared times the z sub k. Then we get a balanced and non-degenerate configuration with capital N equal to 2, n sub 1 equal 1, n sub 2 equal n, p sub 1 comma 1 equal 1, and p sub 2 comma I equal to the a sub I for the I ranging between the 1 and n. So, and here's an example of a genus 8 surface. We also figured out we could combine simple balance equations together. So this proposition tells us non-degenerate balance configurations p sub ki and p sub ki prime of the form 1, n and 1, n can be combined to create a non-degenerate balance configuration p sub ki double prime of the form 1, m and 1, n. And then we can inductively iterate this process. So for example, This figure on the left is a figure for a surface with 8 ends. So I took this 1, 2 configuration and iterated it with a 1, 3 configuration. And then this example with 16 ends here, we're taking a bunch of 1, 1 configurations combining with a 1, 3 configuration. Can also get some nice results for configurations of type 2, n. So here we still got the two levels, capital N equal to 2, but now between the first and second level we'll have 2 necks, so the n sub 1 equal to 2, and then between the second level and back to the first level we'll have whatever natural number n number of necks. So in this case we'll fix the p sub 1, 2 equal to the 1 over p sub 1, 1. So then our polynomial p1 of z will be z squared minus alpha z plus 1, where alpha is equal to the p sub 1, 1 plus the p sub 1, 2, or p sub 1, 1 plus the 1 over p sub 1, 1. And then we get our corresponding differential equation, which turns out is equivalent to Hoynes' differential equation with singularities at 0, infinity, the p sub 1, 1, and the p sub 1, 2 equal to the 1 over p sub 1, 1. For each n bigger than or equal to 5, there is more than one distinct balanced configuration. So here's looking at some of the configurations of type 2, 7. So in these figures right here, I've got 4 of them. So we have the blue ones, those will be corresponding to necks between levels 1 and 2. And then between the levels 2 and back to 1, we've got these orange squares corresponding to the location of those necks. So the example of the surface right here, there's the configuration for that, with the 2 necks, large necks, and then the 7 smaller necks. And here's some balanced configurations of type 3, 4. So there's 4 of them. And this is the simplest ones I found for doubly product surfaces where the location of the necks at the limit, where there's no non-trivial symmetries with their locations.